In this online lecture, we're going to talk about enantiotopic hydrogens and diastereotopic hydrogens and how they appear on the NMR. And here are our key points. Number one, we're going to see enantiotopic hydrogens are chemically equivalent, therefore they give only one signal on the NMR. And number two, we're going to see diastereotopic hydrogens are not chemically equivalent and therefore have different chemical shifts in the HNMR, meaning each one should have its own peak. So let's start with the enantiotopic hydrogens. If a carbon is bonded to two hydrogens and to two different groups, the two hydrogens are called enantiotopic hydrogens. Notice that's what you see here in front of you. You have a carbon that has two different groups, a methyl and a Br, and two hydrogens. And let's call this top one HA, and let's call this bottom one HB. These are your enantiotopic hydrogens. Now, why are they called that? Well, if you replace one of these hydrogens, let's say the top one, with deuterium or anything else, then what you create is an asymmetric carbon. Remember, we learned before in a previous online lecture that these carbons come in two versions, either R or S. And remember, if a molecule has one asymmetric center, then each version is an enantiomer to each other. So basically, replacing one of your enantiotopic hydrogens could possibly create a set of enantiomers. Let's make sure we see that and talk about some vocab along the way. First, let's convert our picture right here into a standard Fischer projection. The first vocab word I'd like you to know is that the carbon right here is considered the pro-chiral carbon. Think of what that means. Pro-chiral means before chiral, which simply means that this carbon has the potential to become a chiral carbon. And remember, chiral is synonymous with asymmetric. So we could think of this as a pro-asymmetric carbon, which means the HA hydrogen happens to be what's called the pro-R hydrogen. That's another vocab word we should know. HA would be the pro-R hydrogen because if we replace him with something else, we'll create an asymmetric center and the specific configuration will become R. Let me show you what I mean by that. Let's replace the HA hydrogen with, let's say, D, deuterium, and let's now figure out the specific configuration. Remember, the Br would be priority 1 and the methyl would be priority 2, so that our sequence would turn from 1 to 2. The deuterium would be priority 3, so we would run from the methyl to deuterium and then back to Br. And remember, in a Fischer projection, the H in this case would be behind the molecule, so if the sequence is turning in the R direction, this would be an R-type carbon. That means the bottom hydrogen here, HB, would be considered a pro-S hydrogen. For the same reasons, replacing him creates an S asymmetric center. So for instance, if we replace him with deuterium, again, Br is priority 1, so we would start with him and move to the methyl, which is priority 2. Priority 2 would then turn to priority 3, which is the deuterium, and then deuterium back to priority 1, Br. If our H is in the top right there, it's pointing to the back, so this sequence is turning to the left, which means the central carbon is an S-type carbon. What we'd like to know conceptually about these types of hydrogens, though, is that they are chemically equivalent, which basically means they react the same way. And in terms of NMR, what that implies is that there would only be one signal in the HNMR for this molecule, because simply these hydrogens are equivalent. So we're noting that chemically equivalent also means that your HNMR equivalent. However, this is not true for the other type of hydrogen that we're going to learn here. These hydrogens are called diastereotopic hydrogens. And let me first show you how to locate them on a molecule. In this example right here, this HA would be one type of diastereotopic hydrogen, and this HB would be another. If a carbon in a molecule is bonded to two hydrogens, and also in that compound there happens to be an asymmetric center, those two hydrogens are considered diastereotopic hydrogens. Notice we have that here. It's this lower carbon right here in the Fischer projection is the asymmetric center. And notice the carbon above him has two hydrogens. These two hydrogens would be your diastereotopic hydrogens. Keep in mind, these hydrogens don't have to be on a carbon that's right next door to the asymmetric carbon. They can actually be on a carbon that's further down the molecule or further away. But let's first understand why these are called diastereotopic hydrogens. It's simply because if you replace one of these hydrogens again with something else, you end up getting a diastereomer. Let me show you what I mean by that. Let's say we replace the A hydrogen with deuterium, you would end up with this molecule right here. Notice in the process we created a new asymmetric center here. Let's now replace the B hydrogen with the deuterium, and if you did that, you would end up with this molecule. Again, we create another asymmetric center. If you were to investigate these two molecules, you would see that they are diastereomers to each other. So notice, by replacing the HA and HB diastereotopic hydrogens, we create diastereomers. Hence, that's why they're named that way. Now, here's what we need to know about them. Diastereotopic hydrogens are not chemically equivalent. And remember, that implies that on the HNMR, they're going to have different chemical shifts or their own unique peaks on the HNMR. Now, let's just make sure we understand why these hydrogens are technically different chemically. This, remember, means that they don't have the same reactivity. Let me show you one example of that. Let's say, for instance, we're going to add an acid to this molecule, which ends up protonating this OH group into OH2+. What we're doing here is simply turning OH into a good leaving group. And then what we're doing is adding a base here. And because we now have this good leaving group, the base can extract this hydrogen, in this case the HA. The electrons here can fall down between these two carbons and in turn boot off this leaving group. If you remember, this is simply an E2 mechanism. If this happens, let's look at our result. We would end up with this molecule right here. And let's notice his arrangement. Notice this double bond is clearly a cis-type double bond. Now, let's do the same type of analysis here, but with the B hydrogen. Again, if we have our OH2 good leaving group, and the base comes along and rips off this hydrogen instead, then again the electrons can fall down here between these two carbons, and we'll boot off this leaving group right here, and we'll end up with this as a result. If this happens, notice the type of double bond we get is a trans-type double bond. Notice, look at our two products here, cis and trans. It's the trans one that would be more favored, and the cis would be less favored. Because remember, the trans double bond in this case has less steric strain and is therefore lower energy and more stable. So think about it. That means if I react a base with this molecule, it's the B hydrogen that's going to be more reactive than the HA hydrogen, simply because the HB hydrogen leads to the more favored product. Another way to think of this is that means this bond right here would be a weaker bond than the HA bond to the carbon. It's weaker because remember, it's easier to rip off the HB hydrogen and break that bond and lead to the trans product. Therefore, this means that the HA and the HB hydrogens are not chemically equivalent. The HB hydrogen is more reactive. This is true for all diastereotopic hydrogens. So therefore, we should expect to see a signal for the HA and a separate signal for the HB on the NMR. So let's put this into practice here. Sample problem. How many signals would be observed in the HNMR for the following molecule? Well, first, let's notice that we have an asymmetric carbon right here. And notice right next door to this carbon to the right, we have a carbon that has two hydrogens connected to it. These hydrogens right here. These would be your diastereotopic hydrogens. Which means now let's try to figure out the number of signals. We'll start here with this methyl and call these the A-type hydrogens, which would make this right here the B-type hydrogens. And now that we know diastereotopic hydrogens are unique, we should see one signal for each one of these hydrogens. So that would be C and then D. And lastly, we have this methyl here. These would be E-type hydrogens. So we should expect to see 5 signals on the HNMR for this molecule. Now keep in mind, this is a very detailed analysis of this molecule's HNMR. If your orgo professor doesn't go over this section, then you wouldn't count those diastereotopic hydrogens as 2 different signals. So you have to make sure your professor discusses this concept before you actually use it on an exam. So what are our key points here? Number 1, we saw that enantiotopic hydrogens are chemically equivalent, therefore they give only one NMR signal. And we also saw 2, diastereotopic hydrogens are the opposite. They're not chemically equivalent, therefore they have different chemical shifts in the NMR spectra.